Hello friends, I'm Nikita and you are watching Prepare for GATE. Electronic devices. This subject contains 3 to 4 questions in GATE examination every year. The questions mostly could be most, could be given in comprehensive type questions where the question might seem a lot lengthy. However, a direct formula based question is often asked. Moving on. Let's see the syllabus. Energy Venn diagram in intrinsic and extrinsic silicon. Carrier transport, diffusion current, drift current, mobility, and resistivity. Generation and recombination of carriers. Poisson and continuity equation. PN junction, Zener diode, BJT, MOS capacitor, MOSFET, LED, photodiode, and solar cell. Integrated circuit fabrication process, oxidation, diffusion, ion implantation, photolithography, and twin process. The topic we are going to discuss is energy band in intrinsic and extrinsic silicon, carrier transport, generation and recombination of carriers, and Poisson and continuity equation. Energy band are the level of band formed when two different atoms comes in close approximation of each other. As the atoms are put together in a solid, various interaction among the atom will balance the proper interatomic spacing for the crystal. The linear combination of the individual atomic orbitals and also the formation of different energy level dependent on the number of atoms brought together. Pauli exclusion principle must be taken care while decoding the energy levels. You can see in this diagram that there are two atoms and whose outermost shell is being combined to give a separate two levels. One is conduction band and one is valence band separated by a band gap. From the given figure, let's assume that the two atoms have one as 6n states and 2n electrons. We can say that the 6n state means the valence shell is a 3 or p, you can say simply, and another having 2n states and 2n electrons. You can say that it is an S shell. In their outermost shell are brought together. When the distance between their states reaches the equilibrium interatomic spacing, these bands split into two, having an equivalent difference of energy known as Eg or forbidden gap. The formed band after splitting will be termed as valence and conduction band, having 8n state, 6n of former and 2n of later, combining to give 4n each. In silicon at 0 Kelvin, 4n electrons will be occupied by the formed valence band, that is the lowest energy band, and the conduction band will be completely empty of electrons and there will be no electrons in the forbidden gap. Metal, semiconductor, and insulator. If we talk about metal, we say that the two bands, conduction band and the valence band, both overlap each other or both are partially filled. For semiconductor, valence band and empty conduction band, there is filled valence band and empty conduction band, and there is a gap of Eg, forbidden gap between both the levels. Insulators have high forbidden gap. The highest forbidden gap could be measured in diamond, direct and indirect semiconductor. If we further differentiate a semiconductor into two, direct and indirect, on the basis of light falling on the semiconductor, then we can say direct semiconductor is when an electron in conduction band can fall into the valence band, giving off the energy in the band gap, e.g., as photon of light. If an electron stable in conduction band gets an energy from the photon incident on that semiconductor, then absorbing that energy, it falls back to the valence band. It releases that amount of energy in the form of light. An electron in conduction band which drops to in the filled valence band can release its energy and falls to an intermediate energy level. That means that the electron on absorbing the photon energy, it doesn't fall back directly or at all to the valence band, because we know in silicon there are 4 electrons in the outermost shell. If you consider that already all the 4 valence band bonds are filled in terms of silicon, then there is no valence band is available or space is available in the valence band. Hence, the electron, rather than falling back to the valence band, it falls to some intermediate level between the two states, termed as an intermediate energy level. Intrinsic and extrinsic semiconductor. There are two types of semiconductor on basis of their purity. Intrinsic semiconductor is a pure semiconductor without any impurity. For example, silicon and germanium. They are also termed as non-degenerate semiconductors. Intrinsic semiconductors have 4 valence bands. Thus, all the 4 electrons take the place in the valence band and none is present in conduction band. Thus, at room temperature, the semiconductor is an insulator. Now, on basis of various impurities, as we already know, that intrinsic is a pure semiconductor and extrinsic is totally opposite to it. Extrinsic is a doped semiconductor. Dope means a mixed and an impurity is added to that semiconductor. Mostly impurities in the form of group 3 and group 5 present in our periodic table are added as dopants. And this whole process is known as doping. As group 3 electrons at group 3 metals have 3 electrons in their outermost shell, so they can accept 1 electron more. To form such type, they are termed as acceptors and added, and in group 5, such as phosphorus, they have an extra electron. Group 5 is a N type and group 3 will be a P type. A N type semiconductor having large concentration of electrons and P type having large concentration of holes. The dopant from group 5, having talked about N type and P type, let's discuss more about them. Doping from group 5 of periodic table induces electrons in the semiconductor. Doping from group 3 of the periodic table induces hole in the semiconductor. Energy level so formed contains the electron near to the conduction band, which is often said to be donor level. Energy level so formed contains the hole near to the valence band, which is said to be acceptor level. As you can see in the diagram below, that in the extra electron are present in the donor level, which are passed to the conduction band, having a imparting a small amount of energy, C minus ED, and add to the conduction band, that is increasing the amount of current. Now EA acceptor level is present near to the valence band. It can drop the electrons into the valence band, imparting further current. Now let's look at one of the question which happens to come in GATE 2017. It says that a bar of gallium arsenide is doped with silicon such that silicon atoms occupy gallium and arsenic site in the gallium arsenic crystals. Which one of the following statement is true? Silicon atom act as p-type dopant in arsenic and n-type dopant in gallium site. Yeah, silicon atom act as n-type dopant in arsenic and p-type dopant in gallium site. Silicon atom act as p-type dopant in arsenic as well as gallium, and silicon atom act as n-type in arsenic as well as in gallium. Now let's solve this question. You can see that gallium arsenide is combined of two element gallium, which is group 3, and arsenic of group 5. Now if we dope a gallium arsenide impurity in gallium arsenide bar, then if we compare these two groups having different belonging to different groups, then we cannot say that silicon act as n-type and p-type. Same in both the groups. This could not be possible. Now the difference lies between whether it acts as n-type in arsenic and p-type in gallium, or n-type in gallium or p-type in arsenic. If we see that the number of electrons present in silicon as compared to gallium is larger, that means a larger electrons present in silicon as compared to gallium. And we know that n-type semiconductors are those semiconductors which contains larger electrons in comparison to holes. Then we can easily see that silicon acts as p-type dopant in arsenic, having less number of holes, electrons and large number of holes, because as comparison to arsenic, which already has a larger electrons, and in comparison to electrons it has less number of electrons and more number of holes. That's why it acts as p-type dopant, whereas in gallium it has larger number of electrons than gallium electrons. That's why it acts as n-type dopant. So answer A, that's our rightful answer. Oh, I have mentioned it over here. Okay, let's see what Fermi level is. Fermi level is the intermediate level in the forbidden band gap where the probability of finding electron below that level is 50% and above that level is 0. So you can see that all the electrons are present below the Fermi level, and above that only 0 electrons are present. Thus, the energy state diagram of the Fermi level you can see in this figure, and the probability of finding the electron is half over here, and maximum it's 1 and minimum it's 0. In n-type material, the large number of electrons in the conduction band moves the Fermi level up. In n-type, the Fermi level is up near to the valence band, because as we know the number of electrons are more and with the dopant being n-type, it has a donor level as well. That's why it makes the Fermi level nearer to the conduction band, because the number of electrons present will be more. In p-type, the large number of holes in the valence band moves the Fermi level near to the valence band. The concentration of electron in conduction band is N0 is Nc e to the power minus Ec minus Ef slash kT, where the effective densities of the state Nc is given by this formula. The concentration of hole in the valence band P0 is Nv into e to the power Ef minus Ev, as valence band is below Fermi level slash kT, where the effective density of state Nv is given by this formula. N0 into P0 would be equal to under root of e to the power minus Eg slash 2 kT is equals to Ni square. The intrinsic concentration of silicon at room temperature is 1.5 into 10 to the power 10 centimeter per cube. This value is often not given in the examination. You can remember this value. The intrinsic concentration of germanium at room temperature is 2.5 into 10 to the power 13. Intrinsic concentration for gallium arsenide at room temperature is 2 into 10 to the power 6. N0 and P0 I have already defined with respect to intrinsic level also. Intrinsic level is that level where no dopant is added and it is almost in the middle of the forbidden gap. If a semiconductor contains both negative charge, electrons and ionized acceptors, and positive charge, holes and ionized donors, then electrostatically neutrality will be maintained by P0 plus Nd positive and N0 plus Nd negative. The mobility of the average drift velocity per unit electric field is mu n is equals to velocity divided by electric field, which is centimeter square per volt second. The current density of mobility is Q n mu n into E. I would say this is for electrons. Similarly, it could be fine for holes also, and the total current density will be Q into number of hole concentrations into the mobility of hole plus number of electron concentration into mobility of electrons into E. E is the electric field, which is equals to sigma into E, which is ampere per centimeter square. And the resistance of the bar is R equals to rho L by. You can calculate rho, which is equals to 1 by sigma into, or you can say L by sigma into A. It will be similar. Now the process of electron absorption or excess charge carrier take place because of thermal absorption and photoconductivity. When a photon whose energy, which is demonstrated by this formula h mu, h is Planck's constant, mu is the frequency, is greater than, which combines to give an energy which is greater than the forbidden gap, strikes the semiconductor surface, the intensity of transmitted electron through the sample thickness I is IT is I0 e to the power minus ET, where A is the absorption coefficient and the photon energy E is equals to 1.24 by lambda. This is impurity scattering and this is lattice scattering. Impurity scattering is due to the T to the power 3 by 2 and lattice scattering is T to the power minus 3 by 2. There are two types of scattering that take place when a photon strikes a semiconductor. The Hall coefficient. When a magnetic field is applied perpendicular to a charge carrying semiconductor F is equals to Q into E plus V cross V, where velocity into magnetic field plus the electric field, when applied on a charged particle, presents a force that deviates the charged particle. A steady state flow of nodes down the electron or down the length of bar, the electric field Ey must balance the product Vx so that the net force is y direction. It should be in y direction is 0. Thus the electric field Ey is known as the Hall effect, and the resulting voltage V equals to EW, called a Hall voltage. The proportionality constant RH is equals to 1 over Q into P naught. Q is the charge value and P naught is the concentration of charge carriers, where rho is equals to Vi over La, which is the direct formula, but if you see, we are actually calculating the charge carriers over here by this proportionality constant, and thus the mobility is equals to the charge carriers divided by, or the whole coefficient divided by the resistivity. These are the various important formulas that we derive from Hall coefficient. What is Hall coefficient is? Hall coefficient is the direct recombination of electron-hole pair. Electron-hole pair are dissolved when an electric field makes the electron to fall from valence band to the conduction band, and it combines with the hole therein, thus releasing a photon on combination. This all happens spontaneously, thus the probability that the electron and hole will recombine is constant in time. Thus, this recombination of excess minority carrier for a p-type semiconductor for a recombination lifetime tau n is equals to 1 upon p naught. Concentration would be del n e to the power t by Tn, where tau n is the lifetime of the electron. Indirect recombination. In indirect recombination, mostly in group 4, which takes place with the release of heat energy, not light energy as in case of direct recombination, heat energy rather than a photon with electron setting from an intermediate state before falling to the valence shell. The electron in this case moves to an intermediate shell or state, and when it gets a empty valence gap, it falls into it, and thus a recombination takes place. The two-step procedure that occur is, first, an electron from the intermediate state falls into the valence band, and to take that place, an electron from conduction band is transmitted to the intermediate state. The conductivity of the sample for semiconductor is Qnt mu n plus P of mu P. Diffusion of carrier. Diffusion, as its literal meaning says, that when excess charge carrier moves from a region of higher concentration to the region of lower concentration. The rate of electron motion can be used in detecting the diffusion coefficient of electron, dn or dt. The net motion of electron due to diffusion is in the decreasing of electron concentration or hole concentration. Qn is equals to minus of dnx over dx, and Qp is equals to diffusion coefficient into the differentiation of hole concentration. The diffusion current crossing a unit area in the particle flux density multiplies by the carrier charge, where the diffusion current density is equals to Q into diffusion coefficient into concentration, into change of concentration of electrons. And you have to keep in point then diffusion current density of proton or holes is negative and diffusion current density of electrons is positive. Now the diffusion and the drift current. On application of electric field, the current gradient will have drift and diffusion current. Diffusion current is because of the minority carriers, and drift current is the major charge current, and diffusion current, both are actually the major charge current. At equilibrium, no net current flow in a semiconductor. Thus, any fluctuation which would begin a diffusion current also sets up an electric field which redistributes carriers by drift. From Einstein relation, we can say that diffusion coefficient upon the mobility of each charge carrier is equals to kT by Q, which is 0.025 volts or 26 millivolts. This is an important relation. Keep this relation in mind, as it's often asked that D is equals to mu of Vt. Okay, at last the continuity equation. The net hole concentration would be, as it moves from x to x plus del x, it's equals to 1 by q diffusion coefficient on x minus diffusion coefficient on x plus del x divided by del x minus del of p upon tau p. That means the recombination rate is subtracted from the actual concentration in the present gradient. At del x approaches 0, the net change in derivative will be equals to the derivative change in hole concentration upon carrier lifetime of holes. Now substituting both the equation, this will give you the expression for continuity equation minus 1 by q change in diffusion density over the change in distance minus the recombination rate. The recombination rate is often given by the recombination rate, which is GOP, in the question, and they will give you the different densities and will ask you to calculate the derivative. The diffusion equation for the hole will be dou del pt over dou t, which is dp upon dpx square minus dou GOP, where LP is the hole. Here I would like to discuss with you all one more equation, that's Poisson equation. I say it a PE, which is equals to the charge density is equals to Q by epsilon over to the charge carrier present, which could be holes minus electrons plus donors minus acceptors. Now this could be the charge density. Now these are the two equations often asked, so keep these in mind. Thank you guys. Keep on solving questions, as most of the questions you will get one or two questions definitely on the concentrations, how to find different concentrations of at the edge level. We'll be talking about that in further lecture tutorial. Thank you. If you like the video, kindly subscribe to my channel and press the like button. Press the bell button for the channel subscription. Bye bye.